It's a winter school, so I have twice as many slides as needed to fill the hour. But I'm really here to answer questions and talk about what you want to hear and about MBE. And this is the first of 3 talks about MBE. So on Thursday, you'll have 2 more talks. You'll hear from Sean O from Rutgers, and you'll hear from Lauren Pfeiffer from Princeton. And Lauren's a real MBE guy. So I've only been doing this technique for 30 years. Lauren's got a couple more years on me. So hopefully he'll pipe up if I say something totally wrong. All right. So please, ask questions. Don't be shy. So let me start by saying, what MBE is, what made it possible, and I'll give you, some oxide examples, oxide quantum materials. Okay. Now, first of all, the technique. In 0th order approximation, this is atomic spray painting. So on the right, I have a cartoon, which is a lie, but at least it gets us thinking in the right direction of what this technique is all about. Imagine that you had a substrate, and you can rain down atoms and build up some layered structure of whatever you wanted. Okay, that's the dream. That's the molecular beam epitaxy. So these spray cans are individual molecular beams, long mean free path. They don't scatter, no atom-atom collisions, no gas phase reactions, no boundary layers. The atoms don't hit anything until they hit that substrate. And if you have the right substrate and you have the right temperature and pressure, you can then think about forming a crystalline layer on top of the single crystal that you start with. So that's the epitaxy part of it. So the surface, the epi, is taking the shape, the taxi of what's beneath it. Okay? So there's the cartoon. Let's look at the hardware over here on this side. This process takes place in an extremely empty environment. So it's a big empty vessel. Stainless steel usually, but the pressure inside is less than a millionth of an atmosphere. And at that pressure, the mean free path is very long. And to generate these molecular beams, elements are heated up inside of crucibles. So this is like an oven. And in front of this oven is a shutter, like a little door that can open and close. And this shutter either allows the molecular beam material that's being evaporated to reach the heated substrate or blocks it from reaching the heated substrate. It doesn't need to be leak tight or anything. It's just a straight line trajectory of this molecular beam going from the source to the substrate. And depending upon what you're making, it might be multi-component, so you might need multiple sources. So unlike PLD where you have one target, a challenge of MBE is that you have multiple elements. You have a different elemental source for each source material that's involved. And you need to get the right mix of elemental sources to reach your compound. MBE is incredibly flexible, but uncontrolled flexibility is chaos, as Chris knows well. Okay, so I have an animation to start things off. Just a fast view of what MBE looks like. First is to bring in some sort of a quartz crystal microbalance to get an idea of what the fluxes are from the individual atomic sources. Then heat up the single crystal substrate to an appropriate temperature where you can have the epitaxy take place. And here you can see the time that it takes for one monolayer, for example, of this material, monolayer of that material, to start building up the structure that you want. Okay. Got the general concept of MBE? Now, maybe one of your first questions is, why do you use different elemental sources for everything? Why not just put yttrium, barium, copper oxide into one of those ovens and heat it up? Anybody imagine a problem if you do that? Sounds like a good way to do it, right? You just PLD. That's what you do. You put YBCO, put it on the target, start zapping, right? Ichiro so showed you that yesterday. Well, let's look at what happens in a thermal evaporation process. I just chose lead oxide, but it doesn't matter. Any multi-component thing in general, when you heat it up, does not evaporate congruently. So the ideal case, you throw YBCO in there, in the crucible, and you heat it up, and these magic YBCO molecules come off, perfectly stoichiometric, and make their way to the substrate. If that was life, it would be fantastic. Right? All your composition control issues would be out the window. You just weigh things out really accurately, and you'd have great films. But things don't evaporate congruently. In general, when you heat up some oxide, the volatile stuff comes off first, okay? And the not so volatile stuff comes off later. The trick in PLD is it's not equilibrium evaporation. It's much closer to a process we call flash evaporation, where you're totally volatilizing everything that is being absorbed in the laser beam. Okay, so just to make this as an example, a concrete example, this is what happens to lead oxide. If you put lead oxide in a crucible and you heat it up, according to thermodynamics, this shows as a function of oxygen pressure what species come off. Okay, so if you're in hard vacuum, so 10 to the minus 15 bar, okay, 10 to the minus 12 torr. I like torr. At any rate, hard vacuum, it looks like this. The main species that's coming off is lead metal. Okay, it's not lead oxide. As you change the oxygen pressure, there is a magic oxygen pressure at which you can get congruent evaporation. But look at all the species that are involved. Okay? And let me point out another problem of this. If you heat this up in hard vacuum, the composition of your source is changing over time. So what you get depends upon, well, was it fresh lead oxide, or that's not what you want in a process. You want to be able to heat up your source and get the same stuff off all the time. Okay? That's why in general we use elemental sources. You heat up an element, you get just that element coming off. Some elements are a little more tricky. They might be clusters. You heat up arsenic, you get mainly AS4 clusters coming off. If you heat up bismuth, you get mainly Bi2 clusters coming off. Okay? But you're getting just the element coming off, and it's not changing your source over time. Okay? Now there are some exceptions to this. Go ahead.
How sensitive is it to the purity of the elements?
Depends upon what you're making. For a lot of quantum materials, Lauren aside, it's relatively insensitive. So in YBCO, you can put, not as much as a percent, but 0.1% of impurities, and you won't hurt TC. Now that's incredibly high by semiconductor standards.
The evaporation rate or the...
Oh no, it's not. Yeah, no, it's just evaporation, right? So you might get some purification over time of your source. Depending if the crud in there is more volatile or less volatile, it can either stay behind or come off first. Okay, so that's a standard way of distilling to purify things. Hopefully by the time you get your source materials, you've already gotten past that stage. I should point out, just in terms of purities, so you're thinking, okay, I'm going to use an elemental source. What's the common purity of elemental source? Many sources for semiconductor use, you can get it to 8 nines purity, meaning 99.6 more nines after that. Okay, it's really, really pure. For a lot of less mature materials, like you might be using for quantum materials, say vanadium, 4 nines is fantastic vanadium today. Okay, so the purities can vary drastically. Okay, everybody got the general picture? Now there are some exceptions to this. Some, relatively few oxides evaporate congruently. A classic example would be silicon monoxide. Silicon monoxide, you put it in a crucible and you can heat it up and silicon monoxide comes off. Other examples along that same example are germanium monoxide, tin monoxide. Okay, so there are very few, but there are a few, okay? Barium oxide is also an example, okay, but it's relatively small. Arsenic oxide, okay, thallium oxide, okay. Generally doesn't work, okay. So you might see something and go, wow, like this is a general trend, and it's not true. Okay, so I've given you the general cartoon of what's going on. Historically, I would say that there were 2 key enablers of molecular beam epitaxy. The first enabler was the recognition by Günther, this fellow in the 50s, about how to make thin films of a material like gallium arsenide, where one constituent is really volatile, arsenic, and one constituent is not very volatile, gallium. Now, it might sound like a real headache. Like you're thinking, how am I going to do that? I've got to somehow get the gallium and the arsenic exactly 1-to-1, right? And this thing's really volatile, and that one's not very volatile. It might sound like standing on your head. And Günther brilliantly recognized that thermodynamics is a great way of making single-phase gallium arsenide using this trick that he calls the, what's he call it? He calls it the Drei-Temperatur-Aufdampfverfahren. So it's a 3-temperature evaporation method. So The three temperatures involved are the temperature of the arsenic, the temperature of the gallium, and the temperature of the substrate. Okay? And what he found, and I'll show you in just a second, was that basically you flood with the volatile constituent, arsenic. Tons of arsenic over pressure. And there's 8 orders of magnitude over pressure that you happily can form single-phase gallium arsenide in. Okay, so forming gallium arsenide, you just flood with arsenic. Okay, if you get too much, more than 8 orders of magnitude too much, eventually you will form some arsenic precipitates inside of your gallium arsenide. Okay, but anywhere in that 8 order of magnitude window, you will form single-phase gallium arsenide. So it's like hitting the side of a barn. I mean, it's totally easy. Okay, and that was a huge breakthrough. The second key piece is ultra-high vacuum technology. And this was in the 50s. Okay. In the 60s, the clever folks at Varian, particularly John Wheeler, developed what's called today the conflat flange. Anybody heard of a conflat flange here? Those copper things that you squeeze on? Okay. That's the sealing technology that was made possible. Let me just show you a couple of historic things. Okay, so first, Gunther never made epitaxial gallium arsenide. Gunther grew polycrystalline gallium arsenide, but it was single phase. And he showed the technique. He also didn't have ultra-high vacuum technology. He was dealing with oil pumps, all sorts of contamination. Okay? It's the combination of the two that really makes MBE possible. So in terms of epitaxial gallium arsenide by the 3-temperature technique, here's the arsenic temperature. Okay? Notice this tube, arsenic is bouncing all over inside of this thing. Okay? Just huge amounts of arsenic. Here's the gallium. The gallium is actually aimed at the substrate. And here's the 3rd temperature, the substrate temperature. Okay? 3-temperature technique. Okay? It works great. All sorts of compound semiconductors. You flood with the volatile constituent, and the growth rate is controlled by the not-so-volatile constituent. So gallium determines the growth rate of the gallium arsenide. Now, you're going to hear much more about this from Lauren Pfeiffer later on, but I just wanted to say the basics of MBE. The second is the conflat, this metal seal technology that is reliable. It used to be incredibly hard before the clever folks at Varian came up with a conflat to have reliable ultra-high vacuum seals. If you have a lot of seals, I'm sure those of you that do any sort of ultra-high vacuum thing are moaning and groaning about this leak and that leak. But imagine the days before the conflat flange, if you can. Okay. So this has got knife edges and all those good things. Now let's come to the technique. The person who put these two things together in the lab first was Al Cho, shown here in this photo. He did it actually in this photo. He did it in the late 60s. Okay, but this is Al in the early 70s on his first MBE at a place called Bell Labs. Now I see a lot of students here. How many people have heard of Bell Labs? Oh, good. Oh, good. It's good to see. It's good to see. Okay, Lauren's from Bell Labs, but anyway, it's amazing how long it takes to grow something great, and how short a time it takes for Judge Green to completely destroy something fantastic. Now, Cornell is very proud to be the first university in the world to do MBE. So I mentioned how Al Cho invented the technique and developed the technique at Bell Labs. In the late 70s, the first university in the world to start doing MBE was Cornell in the group of Les Eastman. Les is no longer with us, but some of his systems still are in his original lab. And the technique is used widely in production. I should mention that Al Cho is actually still around. So this place, Bell Labs, is now known as Nokia Bell Laboratories, and they've torn down some of the building. But Al Cho is still there. He's 80 years old, and he's going strong. And I saw him a couple months ago, and he's doing really well. So he's retired. He no longer has an MBE, but one of the few people that's still at Bell Labs. Okay, so now let's come back to quantum materials. So the technique of MBE was born for gallium arsenide and other 3-5 technologies. It's an incredible technique. It's known for making very precise structures on an atomic layer with incredible physical properties. The highest mobilities, as you'll hear about from Lauren Pfeiffer, who holds the mobility record in the world. I think currently at 37 million centimeters squared per volt second at low temperature. So now the rest of the talk is all going to be on oxides, okay, unless you have questions now. Okay, so let's start talking about oxide quantum materials. the same advantages of these abrupt structures, metastable structures that have been pioneered for semiconductors are also possible to do in oxides. So basically what we do in oxides is we look at literature from 30 or 40 years ago, what people were doing in semiconductors, and we say, hey, I bet we could do that same thing in oxides. So here's an example of a superlattice where we set out to make 1 unit cell of this quantum material, strontium ruthenate, well-known ferromagnet when it's thick, separated by 5 unit cells of this perovskite strontium titanate. Okay? Now you look at this TEM image, and you might go, wow, you know, well, maybe you can't see anything. But maybe you can see that it's a little bit brighter here, and a little bit brighter there, a little bit brighter there. Okay, but is that really 1 unit cell? Maybe, maybe not. But luckily at Cornell, we have a wonderful spectroscopist named David Muller, who doesn't just do annual dark field STEM images, but uses EELs to do spectroscopic imaging of where the rutheniums are. So maybe before you didn't believe it was really 1 monolayer of strontium ruthenate. Notice the strontium is everywhere in the structure. But the distinguishing thing is we want 1 monolayer of the ruthenium and then 5 monolayers of the titanium. And that you can see beautifully in Dave's image. Can we turn down the lights at Cheryl? Is it doable? I have quite a few TEMs, so I just want to. Is it allowed? Are we going to ruin the video? Awesome. Okay, so hopefully you can see that. That's just one example of a quantum material. Here's another example in the manganites. Okay, another superlattice in here with spectroscopy and EELs. Dave's able to look, column by column and chemically resolve what element is involved, not only in little regions like that, but even in much bigger regions like this. And this remains, to my surprise, the world's largest atomic resolution EELs image ever taken. So there's more than 1 million spectra that went into mapping out where all the columns of atoms are. So, okay. So it's possible to use MBE to make quantum materials and have the structural control. But more exciting is to look at the transport properties. So I mentioned in semiconductor structures, the highest mobilities are demonstrated by molecular beam epitaxy, and Lauren Pfeiffer has the record there. Let's have a shameless comparison. This is going to be brutal. Okay, let's have a shameless comparison of what the best transport properties are in, and I chose strontium ruthenate here, from different techniques. So on the left, I've shown the best result ever reported in the literature for the resistivity ratio. This is between room temperature and low temperature in a strontium ruthenate film that's made by pulse laser deposition. Typically, people will have around 5 if you look in a typical paper by sputtering pulse laser deposition. This one by PLD is the highest that's been published. It's at 14.1. And if you compare that to the best that's been achieved by MBE, which happens to be our result, it's 76. So, and I'm just showing one material, please. So the best single crystal today of strontium ruthenate, let me make sure I get this right, is about 100. Yeah. Now that didn't used to be the case. So there's been this back and forth between MBE and crystals. The best crystals used to be around 40. And then Mac Beasley's group by MBE at Stanford showed he could get around 60 in MBE films. Okay, then the single crystal people got back to work and they did even better. They're up to about 100 now. Here and we've now had the record for the film. In calcium ruthenate, we also have the record for a film at 75, and in that case, it's better than any single crystal that's been shown in calcium ruthenate. So, but at any rate, just to say that they're close to each other. Now you might ask why, right? You've seen the technique. I've already pointed out the huge advantage that PLD has is it's fast and it's relatively easy to make a film. Okay, so you don't have to have this magical, cation composition control. What you do is you make a target, you weigh it out precisely, and you start zapping away. Okay, now. That's a plus and a minus. If here I'm showing you the better transport. This better transport comes from better composition control. And you might go, well, how is that possible? Okay, but in this compound, it's like gallium arsenide. Ruthenium oxide is a volatile species. I think RuO3. Okay, and so to make this, we actually supply 3 times more ruthenium than are being incorporated into the film. So we're again using thermodynamics, the same trick that Gunther used for gallium arsenide, to flood with the excess of the volatile constituent and let thermodynamics precisely control the composition and get us to that 113 composition. Okay? And this same trick, I'm only showing one example. The same trick works for lots of other oxides as well.
So it sounds like then that most of the optimization comes from getting the book tonight.
Absolutely. Oh yeah.
But when you're along this years-long process of improving your triple R, where in the process do you start worrying about substrate quality, maybe your target quality?
Purity, maybe. Purity, yeah, fine.
Before, as you're improving, as you're going along, before you really start to tweak your look.
I would say that it's that you try on all fronts and see where you get the most payoff. And what we've found first was the most critical thing was the substrate temperature and getting into what I will call a growth window for this thermodynamically controlled composition, okay? With absorption control. Okay. Now then, once you've found that window and jumped into it, maybe I'll jump to that part of the talk right now. Then you start thinking about the purities. So we're using 4/9 purity ruthenium. You might think, well, what happens if I tried 5/9 purity? And the strain issue, maybe you can already see that in the PLD. This is on gadolinium scandate, and here they have less than a factor of 2 difference. So this is going to be in tension, biaxial tension. This one's on neodymium gallate. This is biaxial compression. So there might be a strain effect. There might also be a quality of the substrate termination. Okay, these are relatively thick films, so these are 20 nanometers and thicker. So then you're continually trying to make it better and better as you get the properties tweaked up. Now I want to come back to your first question I like a lot. It's not. Yeah, okay. So let me jump ahead for a second because I like it a lot. Let's say that you're trying to find out where this window is to make strontium ruthenate by MBE. Now, one way is you go in the lab and you just start shotgun of experiments to try to make the right phase. I don't recommend that. So you're going to waste a lot of resources, a lot of time, a lot of substrates. I think a great way to start is by doing some thermodynamics. So some simple calculations to get an idea of where it is that you might be able to grow strontium ruthenate, or whatever phase it is that you want. Look at the oxidation states that are involved. I want ruthenium 4+. Well, there's different oxidation states that ruthenium can have. It can be ruthenium metal. I don't want that. I want ruthenium 4+. How much oxygen do I need to get to that point? Okay, so the simple kind of thermodynamics that you would start with is to make what an Ellingham diagram, looking at how much oxygen do I need to stabilize a particular oxidation state of ruthenium. And here I've shown, for ruthenium O2, where that is. Everybody, thermodynamics, seen an Ellingham diagram? Okay, I'm calling it an Ellingham diagram. Ellingham actually plotted it slightly different. But the idea is oxygen pressure versus temperature. Where it is, how much oxygen pressure you need at a given temperature to stabilize ruthenium 4+. This diagram says on the line you actually have an equilibrium between the ruthenium metal and the ruthenium O2. Above the line, ruthenium O2 is stable. Below the line is ruthenium metal. Now that would be the case of just ruthenium oxide. When you start to add strontium to the mixture, you're adding an electropositive element. And as if you're a good chemist or good crystal chemist, or if you're Bob Cava told me this important rule, the more electropositive element that you add, the lower oxygen pressure you need to stabilize the high oxidation state. And you see that beautifully in the data. These are all free energy calculations. So this is based on experimental data. And you can see that as you put more and more strontium into this, the amount of oxygen that you need to stabilize the ruthenium 4+ state goes down. Okay, so it exactly obeys what Bob Cava said. Bob Cava says, "Oh, it's obvious." I showed Bob Cava data. It's like, Oh, that's an obvious crystal chemistry rule. I couldn't find it in any book, so I just refer to Bob. Okay, anyway. Often you're trying to make some crazy compound. You don't have free energy data for this, but at least you have free energy data for the binary. So to get an idea of, ruthenium 4+, how much oxygen you need, you should at least be able to do this, to have some idea of where you're going to be. Now you might say, well, what temperature do I need? Well, that's also a good question, but at least you have a map here. As a function of temperature, you can see how much oxygen you're going to need to make this thing. So this is a first start. Maybe you've grown some perovskites before, and you go, wow, to make strontium ruthenate, if I look in the literature and I see what Ichiro's been doing by PLD, I notice Ichiro's been using temperatures in the range of 600 to 700 degrees C to make epitaxial strontium ruthenate. So that gives you a good idea. So even though people used other techniques, it gives you an idea of what's necessary for epitaxy. And now you start looking at the oxygen pressures that are involved, and you might get scared. You look at, wow, it's 10 to the minus 3. 10 to the minus 3 torr. My mean free path is going to be less than 1/10 of a meter. I'm not going to have a long enough distance. Okay, so it's not. You think game over. Okay, we do this with ozone. We use a more activated oxidant to do this. Okay, but now let's take it to the next step. So far, I've shown you what happens in a closed system. So here, I don't have volatility of the ruthenium, but let's add a more sophisticated thermodynamic calculation. So this is what I showed you a second ago. Let's now look at the gas phase and make it an open system calculation where I'm allowing ruthenium loss as ruthenium oxides in the vapor phase. So I'm deliberately supplying an excess of ruthenium from my metal source, is ruthenium metal, 3 times as much ruthenium, in fact, in this thermodynamic calculation, and allowing ruthenium oxides to volatilize. Okay? What that does is it changes things here in the gas phase. When you get above this pressure, about 10 to the minus 4, you can see this definite change here. And this is because you're volatilizing things in the gas phase. This is where you want to be for absorption-controlled growth. You want to be above this kind of a pressure. You want to be in this kind of a regime. Now, what's the colors in the diagram mean? This is the growth window for strontium ruthenate 113. Okay? So from an Ellingham perspective, I was telling you before, you need to be above this line. This is where you don't have volatility. Okay? If you have volatility, it's in this huge window. Oh, it should be easy to hit, and it is. Okay? Let's say you want some other Ruddleston-Popper phase. Maybe you don't want 113. Maybe you want to form this superconductor, strontium 2 ruthenium 04. That exists between this red line and this orange line, or where you have volatility happening between these two lines. Okay? So you can get much more specific of where it is that you're going to go to do your growth by doing a thermodynamic calculation, which I highly recommend. Now we can go a step further. I mentioned the difficulty. These pressures of oxygen are all way too high to be doing MBE. I'll come back to that point in just a second. You don't have mean free path. So you can do it. We call it, what do we call it? Reactive evaporation. Okay? It's a fine technique. It's not MBE. There's lots of gas phase scattering going on. But instead of using molecular oxygen, you can use an activated oxidant. Some people will use a plasma source. Some people will use NO2. So we use ozone, distilled ozone. And we use it because we can distill it to 80% purity when it reaches the substrate. These lines that you see in this diagram are showing the decomposition between O3 and O2. They're saying that if I have 10 to the minus 8 torr of O3 as a function of temperature, my equivalent oxygen pressure lies on this line. You can see the beauty now, hopefully. Notice how many orders of magnitude higher we can reach by using distilled ozone. Okay, now distilled ozone also has its price. It's toxic, it's explosive, it's expensive to plumb it all in. Okay, if the safety officer is across the hall, like he is from our lab, it's an issue. Okay, but in terms of being able to get into this growth window, it's a huge benefit. So now, okay, so we're at this pressure where you want to be even higher. We have tons of marine free path. We have this region. Okay, now knowing that, you can get even closer to it. You start looking in situ by electron diffraction during growth. Well, that's one of the big positives of MBE. It's a low pressure ultra-high vacuum technique. So you can use all those cool ultra-high vacuum surface characterization methods, including in situ diffraction while you grow. Did you guys see that yesterday? Does your PLD have read? You didn't show. Okay. Anyway, but it's cool to be able to see not only the perfection of your starting substrate, but as you start to put stuff down on it, what the reconstruction looks like as a function of growth conditions. For example, here's some example read patterns at different parts of this diagram. Okay, let's look at this. This is a two-phase region between metallic ruthenium and strontium oxide. This is if you read, this is terrible. Right, Chris? Okay. Here you can see that there's a single phase, relatively flat perovskite going on. That's where this transport that I just showed you came from. Okay, it's a pretty big window though. Okay, and so you can play around with temperature and pressure. Okay, but you have an idea based on thermodynamics of where to go. If you want to make the superconductor, you want to be like over here. Okay, so we're growing at 1,000 degrees C to make superconducting strontium ruthenate, which is not trivial. Talk a little bit more about that in a minute. Here you can see it's indeed superconducting. In this system, in other systems, there will be, as the symmetry changes, you could have a doubling of the unit cell. You can pick that up easily and read. So you can navigate where you are in this diagram while you're growing. Okay. Did I answer your question?
Let me follow up.
Please.
Not wrong. So then you have a sort of a map.
Yeah.
So you start and then you maybe say oxide, I know what traits.
Yeah.
How long does it take you to get to this point where you can come back and say this is
We've done this a lot, and I would say it takes us a year. Yeah, is that fair, Chris? Joe CN? I have some people here to keep me honest. Joe CN? So we've done a lot of these, where'd you go? Oh, good. We've done a lot of these volatile systems. It's true in iridates, too. So strontium iridate, barium iridate, ruthenates, they're great systems where you can flood, and it might seem weird. I'm talking about iridium being volatile. And it's not volatile as a metal, it's volatile as an oxide. And so the same game that was played with gallium arsenide by Gunter back in the 50s, you can play in oxides and to get automatic composition control, which is a huge deal. Yeah. But it's slow. The technique MBE has many meanings. One of them is many boring evenings. Okay. Okay. Maybe you'll hear more from Lauren on that. Let's come back to a second. I want to talk about the mean free path issue. So a key issue that came up a few minutes ago was trying to make my oxide, and I need, from thermodynamics at least, a pressure that's really high. Have I lost my mean free path? Okay, so here's a calculation of looking, and this is basically for all the different elements in the periodic table as molecular beams, of as you crank up your oxygen pressure, what the mean free path is. Okay, now it depends upon how big the atoms are in the atomic beam that are colliding with the oxygens. Okay, so if you have a really big atom, like barium, okay, where you hit this limit, so in a typical MBE system, you have about 20 centimeters between the crucible and the substrate. Now maybe you're going to make some sort of a nano MBE, maybe it's possible, okay? And then those distances could get smaller, but for basically your standard MBE system, this distance is about 20 centimeters. So that means that I'm limited to, if I want to have this long mean free path, I'm limited in the pressures to things that are less than about 10 to the minus 4 torr, okay? And a minute ago we saw, I'm at 10 to the minus 3, big problems, okay? Now, and it changes slightly depending upon, if a small atom like lithium, okay, it gets slightly long. Instead of being 10 to the minus 4, it's 2 10 to the minus 4. Big deal, okay? But that gives you an idea. All sorts of other nasty things start to happen, though, at 10 to the minus 4. At 10 to the minus 4 torr, you have, your hot filaments, like all these fusion cells. You're starting to burn them up, okay? So all sorts of other bad things happen. It's a big advantage to be able to go to low pressures if you can form your oxide. Okay, so that's one aspect. This aspect I sort of got at a minute ago. I was talking about how to form ruthenium 4+. Okay. Well, some elements are really easy to oxidize and other elements aren't. That's the beauty of an Ellingham diagram. So here I'm just showing a bunch of different, so somebody asks me, well, do I need to use ozone? Well, it depends upon what you're growing. If you're growing barium oxide, no. Oxygen works just fine. If you're trying to make bismuth oxide or some cuprate, hell yes, you need to have a more powerful oxidant to do MBE. Okay, so thermo is very useful. Questions? Okay, so it's not random. The synthesis conditions are not just random. You do your homework first before you start using resources in the lab. Okay. Doesn't mean it's going to work, but at least you give it a try. Let's come back to cuprates for a minute. So here's a great quantum material. Cuprates, if you're just getting started, you can easily do an Ellingham calculation for where it is that you need to form copper 2+. If you look at real compounds, here I've shown a bunch of cuprates. They're relatively close to that line, okay? But indeed, different compounds are slightly different of where you need to be. And for just about all of them, you need ozone, okay, or some activated oxidant. Okay, I already went through this example, so let's get through that. Okay, so I've been talking about a lot of synthesis rules in terms of making things, and I thought how it's important. It's important to know the synthesis rules. We spent a lot of time talking about different synthesis rules. Here's some of the more important ones for quantum materials. So hopefully, it's good to have thermodynamics on your side. There's this fellow Bernd Matthias. Did you know Bernd? Barely. Okay, at least you knew him. Now he had his own rules. So it's not only important to know the rules, but it's important to break the rules. So I'll give a couple of examples here. So first, Professor Gibbs, famous professor from Yale, thermodynamics. Now, let's say that the quantum material that you're really interested in is this one over here. But that Professor Gibbs says that this is the one that has the lowest free energy. Isn't that a bummer? It seems to be always that way. Okay. Now, one way of changing that is what I'd call breaking the rules. And in truth, I'm not really breaking the rules. I'm just redefining the thermodynamic system to include the substrate. So maybe as a bulk phase, this is the one that has the lowest formation energy. But if I change the system to include now a substrate that is specifically chosen to have the same motif as the phase that I want to stabilize, I can make this a very low-cost interface compared to the same substrate, when paired together with what was the stable phase, the energetics of this interface can change this balance, if this balance is close enough, to be the other way. Okay? Now, I'm not saying that I can make anything, which is very important. So when Professor Rabe does calculations to say, here's a really cool material if you could make it, it may be that it's this phase over here, but it's so far that even by using this trick, you can't epitaxially stabilize that. And to give you an idea of how far that is, it's roughly 50 millivolts per atom, roughly, of how much you can tip this balance. Now, in oxide systems, there can be a lot of competing ground states that are within around 50 millivolts per atom of the ground state. And that can be really exciting. If one of those has incredible properties that you're going after, this is a great trick. It's called epitaxial stabilization. But I want to emphasize, it's not just the thin film on its own. Okay? The thin film on its own, wants to make this. You can't do that. It's the combination of the appropriate substrate with the thin film. And here's where I think a lot of progress can be made in targeting cool properties. But you need to have a friend or the ability to make a single crystal that has the right structure for what you're trying to pair it with. Okay? Okay, everybody got the idea of this trick? I'll give you an example, I think, maybe next. Okay, so it's that interfacial energy. In terms of examples, I'm going to show another ruthenate here, another quantum material, barium ruthenate. Okay. So this is from the bulk literature. Barium ruthenate, the ground state is this rhombohedral structure, like this. But let's say that you wanted to make the perovskite form of barium ruthenate, like John Goodenough did recently. So in this paper, John Goodenough used 180,000 atmospheres of pressure to stabilize this phase. Okay, good for him. He made it in polycrystalline form. Okay, and he can in fact, stabilize it at only 30,000 atmospheres. He can stabilize that. Okay. Well, let's say that, and indeed it's ferromagnetic. It's, interesting in terms of the properties. So this is one route to accessing those other ground states, pressure. I want to show the thin film route. The thin film route is to pair it together with a substrate that has the same kind of structural motif, a perovskite. Okay, so we're thinking, okay, barium ruthenate, here's its lattice constant, and now I want to pair it with a perovskite. Here's all the commercially available single crystals of perovskites, and if you're a perovskite aficionado, you might recognize a lot of these as not being cubic perovskites. They have octahedral rotations in them. So the cubic perovskite that we've paired it with is strontium titanate over here, which has got a considerable lattice mismatch. But nonetheless, as long as you make the film thin, so less than 5 unit cells, it forms this cubic polymorph, which took 180,000 atmospheres in bulk to stabilize. We can stabilize it as a thin film. And it's thick enough, although it's quite thin, it's thick enough to do things like photo emission on. So Kyle Shen's group has done angle resolved photo emission, been able to make transport measurements on it. Okay, so you can stabilize phases using this trick.
So that's a compressive strain?
This is in biaxial compression. Yeah, correct. And that might be...
Can you compare the kind of pressure the strains?
Okay, so the hydrostatic versus biaxial are different strain states. People usually, give me the question, well, what's the maximum pressure you can put on in terms of thin film? So I showed this is like, okay, 180,000 is really big, but it's not. They're really different things. They're really different things. So one's one's biaxial and one's triaxial. So, anyway. So 399 in plane is what it is in bulk, and it's cubic. And suddenly we're putting it on strontium titanate, which is 3905. So it's a huge biaxial compression, and now it gets longer out of plane. And that could be what's responsible. There's no longer a magnetic transition. So in bulk, you saw at 60 Kelvin, it was ferromagnetic. We don't see that. And is that a finite size effect, or is that because of the biaxial strain? So we're developing more substrates. It seems like we never have enough substrates. So we're developing a new substrate that's cubic, and it has a lattice constant of right about here. Okay. So in a couple of months, I hope to be able to better answer that question. It'll allow us to make thicker films and get away from the finite size question and look at the effective strain. But this is I think it's an exciting opportunity to pair bulk and thin films in substrate film combinations. Okay, now the other famous rule, which I think is outlived its time, is Matthias's rule. Here I show you his different rules for finding superconductors. Many of them are known to be wrong, for example, for cuprate superconductors. And I'll claim that this last one has outlived its time. And I urge you to break the rule. And instead of distancing yourself from theorists, at least the best thing I ever did was start talking to and listening to theorists. So here I give some examples. Here's Karen. Nicholas Spalding. Okay. Anyway, but not only to not stay away from theorists, but also to provide them with useful feedback. So it's and I think as you'll see in Karen's talk, that a very powerful input coming from theory is what the electronic structure of your quantum material looks like, at least according to calculation. And it can be very useful to provide theorists with what the electronic structure looks like from experiment. So being able to provide particularly the electronic structure from a technique like ARPA's is a great thing to do. And I want to say a few more words about this in my last 15 minutes to talk about this connection between thin film synthesis and ARPA's in the realm of quantum materials. Okay, fine. I'm happy to. I could talk forever, but I'll. So in terms of combining MBE with photo emission to see the electronic structure, it's something that we've done at Cornell, and I'm happy to say that we were the first in the world to do that for complex oxide MBE. And in terms of the hardware, I've shown you, I've spent a lot of time talking about the MBE part of this. And the photo emission part of it is connected under ultra-high vacuum. I'm not sure if you're going to have a photo emission on ARPA's talk. I don't think I saw it. Anyway, but there are experts in the room. So but in the realm of quantum materials, it has a big impact on what quantum materials you can study and figure out their electronic structure. So in the old days, in studying quantum materials, if you wanted to determine the electronic structure, you needed to have not only a single crystal, but you needed to have a single crystal that cleaved. And that's a relatively small part of the universe of quantum materials. And it's very challenging. Imagine having a much bigger universe to search in. And this universe is made possible by the combination of a thin film technique where I no longer need the surface to cleave. I no longer even need the material to be a stable material. It can be metastable. It can be one of these ground states that I've accessed through this trick of epitaxial stabilization. It can be a superlattice. It can be a one monolayer of something on top of something else, an interface material. Okay? So I'll claim that the universe of artificial quantum materials is now huge because I no longer need to make a single crystal that cleaves. Instead, I can use all of these thin film tricks that I've spent a little bit of time talking about, like this strain engineering part, superlatticing, like I showed you before, making these metastable phases. And I've listed for each one an exciting quantum material that I'm sure you've heard about that utilizes that particular trick. And now you can see the electronic structure by having this combination of ARPAs together with a thin film technique. I don't need it to cleave because the film's already flat. So, okay, so hopefully you see the advantage of this approach. And if you have that approach, you can think generally of how you could tweak a particular structure. So I would argue that the way that most quantum materials are discovered today is they're isolated points. I have this quantum material, maybe I change an element in my quantum material and I go to some other quantum material. As opposed to tweaking a particular phase. By tweaking it, I mean, what happens if I bring the atoms a little bit closer together? If I change their distance, for example, by using a substrate that has slightly smaller lattice constant or slightly larger lattice constant, I can change the overlap between my orbitals. Or maybe I want to change the doping on this axis. There's a bunch of different axes I could put on this plot. But I could start from a single phase, and I could start to think about what happens when I tweak it in terms of how its electronic structure evolves. And that's something that's, I think, very tractable to theory. As opposed to saying, well, okay, I made the strontium analog, now I'm going to put barium in it. With some point that's over here. Okay, now I'm going to put, I don't know, lutetium in it. We're going to be moving all around with individual dots. And this can be fun because often, the interesting ground states that you want are often at the between where the material goes from being metallic to insulating. And if you can tweak a particular ground state, you can start to explore what happens in different directions in this multidimensional space. I mean, this is a simple cartoon that I'm showing you. Okay, so I'm imagining, being able to tweak by these parameters. And I have a particular example that I'll end with on this. And the example that I want to show tweaking of is the superconductor strontium ruthenate. Okay, so here's a ruthenium 4+ compound. Maybe you've so it's it's well known to be superconducting. I'll skip through the introduction. In single crystals, it's well known that if you tweak the material by applying uniaxial strain, so this is work from Andy McKinsey's group, where he's applied uniaxial compression to strontium ruthenate, and he's shown that he can double the transition temperature. So it goes from having a transition temperature that's about 1.5 Kelvin here at 0 strain, and if he tweaks it by uniaxial compression, he can more than double the transition temperature. That's a very exciting thing. I also want to point out that notice when he puts it in tension, this is a ceramic material, it fails in brittle fracture, so it cracks. Okay, so there. Okay, anyway, it's a very nice map. And what Andy has done is to he can't see the electronic structure directly, but he has collaborators that do first principles calculations, and he thinks that he's changing this so-called gamma band to be closer to the Van Hoff singularity by applying this uniaxial strain, and that's what causes the increase in the transition temperature. Well, let's see directly what's going on in ARPAs by applying biaxial strain by changing the substrate. So this is an example of tweaking this phase and seeing the electronic structure. So it's the same trick that I've been talking about. Strontium ruthenate has a lattice constant that's over here. The strains that are possible in film land are much larger than what you can do in single crystals. So I'm going to start off by showing 0.9% strain to strontium titanate substrates. This is what, from angle resolved photo emission, the band structure looks like, or the Fermi surface looks like for unstrained strontium ruthenate. And now let's have a look at how that changes when it gets put on strontium titanate. If you couldn't see the animation here, I have them side by side. But notice how this gamma band is getting closer to the edge of the Brillouin zone. So this gap here is smaller than that gap over there. Okay, and you can see that directly now, looking at the electronic structure. So what happens if we go further? You might think that what was an electron pocket here for this gamma band might eventually turn into a hole pocket around the X point here as it goes through the Lifshitz transition. So that's what we set out to do. So we set out to make strontium ruthenate thin films not only on top of strontium titanate substrates, but on top of these even larger substrates and see what happens. Now, unfortunately, the substrains are getting larger here. Unfortunately, at this large strain, what happened was when we grow strontium ruthenate on top of the substrate, it relaxes immediately. So that's a bummer. So what we did was we switched the chemistry slightly. We kept the ruthenium oxide planes, but we switched from strontium to barium, which is a larger lattice constant. The ruthenium oxide plane is staying the same. So in thinking about this, of what's happening to this, how we're straining the ruthenium oxide plane, it looks just like this number line that I'm showing. And now I'm going to show you going from the strained strontium ruthenate to the barium ruthenate 214 that's strained even more. What was an electron pocket here has indeed become a hole pocket. So we've gone through that Lifshitz transition. So we're tweaking a phase. Here, these are energy cuts from ARPAs, and you can see this band crossing the Fermi level as we go through strain. Okay, so this band that you see here, as we march along in strain, you can see how you can tweak that phase. This has become of interest to our theory colleagues. Here's a preprint they have on the server, where as a function of strain, they're looking at what they expect the transition temperature. I'm told that this axis, this vertical axis here, which is something that only a theorist could love, is it has something to do with the TC of the material, and that as we get close to the optimal strain, that indeed we should see a drastic enhancement of the transition temperature from biaxial strain. So we're eager to work on that, and maybe there I'll stop for some questions.
In Andy's experiment, there's a maximum at, I don't know what the strain was, but it was a fraction of a percent.
Correct.
So is that, are they saying that this,
Well,
is that behavior, or?
No, they've calculated the biaxial strain case.
Oh, I see.
So they've calculated what's appropriate for films as opposed to Andy's case.
But
Yeah.
do they consider the uniaxial case?
Not that I know of. You'll notice this for the biaxial case also has a peak.
Yeah.
So
that's where the Lifshitz transition.
Correct. So it's very close. From a symmetry perspective, Una says that it cannot be an odd triplet right at the Lifshitz transition. So she suggests coming close to it, because we want to have this odd parity topological superconductivity. Okay, so we want to she says come close, but not exactly right to the Lifshitz transition. Okay. Maybe that's a good place to answer questions.
Okay.
You say I should stop.
Yeah.
Okay.
Thanks, Darryl.
Sure.
Time for questions. Yes.
What would you say are the advantages or disadvantages using grown layer strain versus the
Okay. One advantage is that in the grown case, you can access higher strains. So another advantage is you can more easily access the electronic structure, as I've shown you from this approach. Disadvantages. It used to be a big disadvantage was that films of strontium ruthenate were not superconducting. Okay, and that was a huge disadvantage. That has changed relatively recently. So I'll show you that the history of superconducting strontium ruthenate films. So the first superconducting strontium ruthenate film was 7 years ago. This is made by pulsed laser deposition. So Kawasaki's group in Japan showed in one sample that they could make superconducting strontium ruthenate. That student, Yoshi Krokenberger, then went on to NTT, and the group was unable to reproduce the result. This is Cambridge, also by pulsed laser deposition, more recently from Judith Driscoll's group. And she showed that the superconductivity was localized in her samples, inhomogeneous. Okay, so you can see this kind of all over the place transport, but some regions where it looks like a superconducting transition. Now more recently, this is again from Kawasaki's group in Japan, using MBE now instead of PLD. They can reproducibly, so here you see 3 different samples that are reproducibly superconducting, and even we can now make superconducting strontium ruthenate samples. And let me point out the temperatures at which our superconduct are much higher than anything that's been shown in the past. Okay, these are unstrained. Now we want to have some fun with strain. Okay, so I think that it's coming together to have that superconductivity and the ability to strain it.
So these resistivities are quite high, though, compared to the bulk.
Oh,
In other words, if you made bulk strontium ruthenate with 3 microcentimeters,
yeah.
it would never be superconducting, right?
The
I'm talking about the impurity
yeah,
scattering.
it's true. The triple Rs that are needed in single crystals are about 80 before you start to see superconductivity. And the triple R, for example, of these films are about 4, where inhomogeneous superconductivity comes in. These have about 20, or no, here we go, between 22 and 30, okay? And our films have a max of now, we've gotten up to about 50 in triple Rs. So it is, you are right, that in single crystals, it's even higher triple Rs that are needed. And I think the films can still be improved, but we do see superconductivity.
So is there some other factor that's not being considered then? My question about impurity scattering?
No, I would say it was the opposite. So in single crystals, you need to be very concerned about the purity of the material, as we do in films. And a few hundred parts per million of impurities can destroy superconductivity. We made films 20 years ago that had less than 100 ppm of impurities, and they were not superconducting. And the disorder was not from impurities, but rather from out-of-phase boundaries in the films. And we could see those by TEM. So we had other defects, and that's what I think is really limiting here. So in a TEM, you can see that these out-of-phase boundaries are getting further apart. They get further apart by going to high substrate temperatures. So we're growing at 1,000 degrees C. So very high substrate temperatures, you grow this structural disorder to be further apart, and we have less than 100 ppm in our materials. Yeah. Please.
So let's say you're combining 2 different species in your MBE, one that does not oxidize at all, the other that over-oxidizes.
Yeah.
How do you go about choosing what kind of conditions to use for?
It sounds like you don't have thermodynamics on your side.
You got to break the rules.
Very hard, very hard. So I guess the closest, yeah, I like that. I like that. The closest would be to try to put you got to get the order right. So you put the one that you want to oxidize down first. Then you go to very low temperature. And do I have this right? One of them, tell me again, one of them doesn't oxidize, and you.
Let's say you are trying to
Yeah, I like that. Okay. Okay, so the way I would do that, and I know both materials, is I would form the copper oxide first, high temperature and fully oxidized. Then I would cool it way down. Europium oxide we can grow at room temperature. So I'd go way down in temperature and now use so I'm using kinetics to limit the decomposition of the one that's really hard to oxidize. So then I can put down the one that I don't want to oxidize too much on top of it. Yeah. If you take it up, no, for europium oxide, I use molecular oxygen. Yeah. So you would change your oxidant species and use kinetics to get around. But if you needed a multi-layer, it becomes more difficult. Because if you want to heat that thing back up, the europium oxide would love to steal, europium monoxide, would love to steal its oxygen from the copper 2+ and form Eu2O3. So if you look from an Ellingham perspective, you go like, you got no chance in the world of this happening. But you can play kinetic tricks with this. Yeah. It's the same kind of trick that we use to grow strontium titanate on silicon. It's again a kinetic trick.
I have another question. So you have this beautiful spectrum of substrates that you can choose from.
Yeah.
But can you talk about some of the practical difficulties in that? I mean, for instance, you have crystals. Is there issues with forming nice surfaces to start with and so on? What's the limitation?
Yeah, absolutely. So the problem initially was just the substrates. So but a substrate is just the beginning, because not only do you want to have a high quality substrate, and in perovskites we're lucky now to have about 20 different lattice constants of high quality perovskites, but now you want to have a well terminated substrate. You want it to be smooth. You want to know what that termination is. So strontium titanate has been around the longest of the perovskite substrates, and it has the best known chemistry to etch it and give it a nice termination. And that was done by Kawasaki's group and then refined by the Twente group in this paper, even for different orientations of strontium titanate, so they look nice and beautiful like this. Of those 20 different substrates, there are not that many for which there are these chemical termination recipes. So I'm showing you a cartoon. Well, I'd like to know what the substrate's terminated with. Is it terminated with the AO layer or the BO2 layer? And for many substrates, you don't know. And it's got a mixed termination, and that makes your growth more difficult. So it's desirable to have not only substrates that are of high quality, but also to know their termination and have these recipes. So that's an area that needs a lot more. It's wide open for people to do more work on. On the substrate side, I'm happy to be part of a collaboration that's doubled the number of perovskite substrates in the last decade. And we keep adding more at about a rate of 1 per year. But if you look at other systems that maybe you're interested in oxides, pyrochlores, there are 0 commercial substrates in pyrochlores. In spinels, there's 1. So I mean, there's all these other oxide systems that you might be thinking of playing this game in. There's a need for more substrates that have well-controlled surfaces.
I remember you wanted to mention something about paradigm.
Yeah.
Please do that, and then we'll...
Okay. Awesome. So I want to give you a shameless advertisement. So you're here at this quantum materials school. You're getting to see great techniques. Maybe you're wondering where is it that you can actually do this if you're lacking some of these facilities. And I want to point out to you that there is a new platform in NSF language dedicated to helping people like you make cool new stuff. Okay? And that's called Paradigm. It's the platform for the accelerated realization, analysis, and discovery of interface materials. And NSF gave us a huge pile of money. And I want to point out that more than 69% of this money is for users. So it makes it so that with a 2-page proposal, people like you from academia can use the facility for free. And things that are in the facility, we have 4 different facilities, and it fits well with what you're seeing here. We have a facility that will help you do theory. We have a facility that will help you do bulk crystal growth by floating zone and other techniques, Tchaikovsky, Bridgman, vapor transport. Thin films includes MBE, ARPAs. and electron microscopy. You can cut me off whenever you want. Let's have a look at the single crystal growth facility. This is not far away at Johns Hopkins. So Tyrell McQueen runs the facility. And what's unique about it is not only does he have a multitude of different floating zone systems, in fact, the largest collection of different types of floating zones in the United States. He has the world's highest pressure floating zone. At 300 atmospheres, it's more than twice as high as anywhere else in the world. And at that pressure, some of the gases become supercritical. So argon, carbon dioxide, oxygen all become supercritical, so that not only can you access these ground states that require pressure to form, but also the stability of the growth can become better when it's growing inside of the supercritical fluid. So here you see sapphire growing inside of oxygen at higher pressures, up to 250 atmospheres. Also laser tilt pedestal growth, induction heating. Okay, so high temperatures are possible in this facility. In all of the facilities, Paradigm has staff to help train you to use the equipment and not break it. But it's not their job to help you realize your wonder material. You provide the labor. Okay, so it's a user facility. So everything that you make belongs to you, which is good. Okay, it's like going to use the clean room. You know, you show up, we show you how to use the tools, and then you have some fun. On the thin film side, we have a new MBE courtesy of NSF, and we're allowing 62 elements of the periodic table in that MBE machine. So here you see our periodic table. Everything it's dark there, we're allowing in the MBE, 11 at a time. So it used to be that Ichiro was the only place that you could do lithium, because nobody would put lithium in their MBE machine, and including me. So in 30 years, we've put 43 elements in our MBE machine, and can still make superconducting samples. But in Paradigm, we're going to put all these things in there. So 62 different elements, quite a stretch, but it's going to be fun for materials discovery. On the electron microscopy side, this facility is also at Cornell. My colleagues have developed a new detector for electrons, and which gives rise to new imaging modalities and incredibly high resolution images. So the beauty of the new detector, which was first developed at the Cornell synchrotron by Sol Gruner and then ported over to TEM by David Muller, it has an incredible signal-to-noise ratio. It captures all the electrons that go through the sample, both the direct beam as well as all the diffracted beams at the same time. And by doing that, as the beam is scanned across the sample, it allows traditional imaging modalities like bright field or dark field, where you reconstruct the image from the diffraction pattern. But because if you have some sample that has different lattice constants, like here, this is a two-dimensional material where in the plane of this one monolayer thick sample, the lattice constant's changing. By mapping changes in this diffraction pattern as you move the beam, you can have this lattice constant map of the sample. And you can have new imaging modes, like looking at the strain map once you have this imaging. By collecting all the beams at the same time, it's also possible to do tychography on the images, which is utilizing the phase information that you get from all those diffracted beams. And here I show you real data as the electron beam is scanned across this two-dimensional material. And here, using a conventional detector, this is a commercial FEI detector, versus this new detector, I hope you can see the difference in image quality. There's a defect in this image, and that defect is much easier to see. This is a transition metal dichalcogenide where there's one monolayer of the material, but there's two sulfurs in this monolayer. And here it's missing. It's much easier to see in this image than the other image. Dave claims that the resolution with his new detector is drastically improved. To prove that, Elena Korkoutis took a single crystal that was made in the single crystal facility by Tyrell McQueen's group. And the distance between this dimer is only 0.67 angstroms. And you can easily resolve that experimentally with the new detector, as it's quite difficult to do with the old detector. It's also a theory user facility. And in total, I just want to remind you, this is free to academics. We also have summer schools in theory, in crystal growth, every summer. I encourage you to apply. I encourage you to become a user. It just takes a 2-page proposal. Anyway, it's my shameless advertisement.
All right.
Thank you. Thank you very much.